Hello, science enthusiasts. Welcome to Science Chat. Every week, we bring you an amazing expert to enthrall you with their area of knowledge. Today is a special Science Chat panel where we have not one, but three experts. We have Amanda Bachman, we have Mairead Montague, and we have Jeremy Mettler. They are all nuclear experts and in a different area of nuclear science. My name is Jason Zakowski, aka Dad Guy.
And the co-host is Chris Zakowski, also known as Mummy Fave.
My co-hostess with the mostest.
There you go.
And what we're going to do is have a panel discussion with some Q&A. So Amanda, Mairead, Jeremy, what I'd like you guys to do for the panel is to refer to each other by your first names. So if you want to interject, go ahead. If you want to, answer a question, go ahead. If two people talk or three people talk at once, that just means we're really excited about what's going on, and that's okay. All of the questions the questions I'm going to pose, I'm not posing to anybody in particular. I'm posing to all of the panel at the same time. So this is not going to be like one of those stuffy conferences where somebody asks a question and then we go down the line and everybody answers it in turn. It's going to be more interactive. Now, everybody on the panel has a slightly different expertise in different areas. Now, this is where we're going to go one at a time, just so we can do a little introduction. So just because Amanda is first on my screen, Amanda, could you introduce everybody to who you are and what you study with nuclear science?
I would be more than happy to. Thanks for having me. So hey, y'all, I'm Amanda Bachman. I am currently a graduate student at, at the University of Illinois in Urbana-Champaign, working on my PhD in nuclear plasma and radiological engineering. My current research focuses on the nuclear fuel cycle, which is just kind of a fancy way to describe how we get uranium out of the earth, how we process it into a form that we can use as fuel for our reactors. And then once it comes out of the reactors, how do we do the waste management part of it? So that's my current research. Some of my previous research has also focused on non-proliferation safeguards with respect to the nuclear fuel cycle. So how can we make sure that no one that isn't supposed to have nuclear material doesn't get access to that material?
Okay, cool. All right. Amanda, thank you so much. And thank you so much for being on our panel today. Really appreciate it. Mairead, over to you.
Hello. So I'm Mairead Montague. I'm about to be a fifth year graduate student, getting my PhD in nuclear engineering. I'm about to start wrapping that up. And my research is in radiation detection. So Amanda and I have work that sort of attacks the problem of non-proliferation from opposite ends. Amanda looks at the fuel itself. I design the detectors and some of the systems that will be used to try to verify what's there. So I do a lot of nuclear security work and create all the detectors help create all the detectors for ports and to prevent things like illicit diversion of nuclear material.
Thank you, Mairead. All right, over to Jeremy.
Thank you for having me. My name's Jeremy Mettler. Like Amanda, I'm a graduate student at the University of Illinois, also in my going into my fifth year. I'm on the other side of nuclear science. I study plasma science, so this really energetic state of matter, which exists in stars and in lightning and all sorts of places naturally. My area of research is specifically in how we can use this state of matter to try to modify things like solids and liquids to make them more useful for us. So the interaction of plasma with the other states of matter.
All right, nice. Thank you, Jeremy. So we've had a little introduction. I'm going to give you guys all a like a icebreaker question, though, to start. Now, you weren't prepped on all of this. So, Amanda, Mairead, Jeremy, take your mics off. Okay, are we ready? Okay. All right, take your mics on, I mean, not off. Turn your mics on. All right. Okay, Dog or cats?
Dog.
Cat.
I say dogs, but I think we all know I'm a rabbit person at heart.
That's true.
Okay. Ride a dinosaur or ride a wolf?
Dinosaur.
Wolf.
100%.
I would so rather ride a wolf.
Okay. Spaghetti or lasagna?
Lasagna. Cheese.
Spaghetti.
Lasagna.
Okay. Favorite ice cream flavor?
Mint chocolate chip.
Dark chocolate.
Chocolate peanut butter.
Okay. Mint chocolate chip? That's amazing. Okay.
It's so good.
Okay. All right. Skydiving or scuba diving?
Skydiving.
Scuba diving.
Can I say both on this one?
Yeah, you can say whatever you want. Okay, last one. Now, what we're establishing is that there's no pecking order to speak, and it sometimes takes a little bit of time when there's a bunch of people at one time. So we're not even talking over each other, and if it happens, that's okay. Okay, favorite breakfast cereal?
Raisin bran.
Oh, Honey Bunches of Oats for me.
Any bunches of oats? Okay.
I don't really do favorite breakfast cereal. Like, we never had cereal growing up, but now my guilty pleasure cereal is Captain Crunch, and I'll sometimes just have it for dessert.
Capitan Crunch. Okay. All right. So we've all learned the most intimate details about our nuclear experts. So it's time to get on with the show and talk a little bit about nuclear science. Now, the first question is a pretty broad one, and I'll let the panel go in whatever way they want, and anybody can jump in and you can bounce ideas off each other. The first question is, how does nuclear power work?
I guess I'll start on this one. So a lot of people tend to be familiar with like old power plants or natural gas plants where you physically burn the coal or the natural gas, you create some steam, use that steam to turn a turbine, and then that turbine spinning creates the electricity. Nuclear power, when you take it as, in terms of like energy, it's the same general process. We just use a different method to make the heat. So instead of chemical and combustion reactions, we're using nuclear reactions. Specifically, we're just splitting uranium atoms in half. So that creates a lot of energy, and that's how we create the steam.
Okay, where do you get nuclear fuel from, though? Like, how do we get that fuel?
Yeah, so we can actually. Oh, go ahead, Marie.
No, you can go for it, Amanda.
Okay.
Your fuel cycle. I'm just end of life fuel cycle.
Okay, yeah. So we actually just mine uranium out of the earth. It's a natural ore deposit, just like you find, aluminum or gold or iron or anything like that. The fun part is, like many minerals, uranium is not evenly spread out around the Earth's crust. Actually, Canada has some of the largest uranium deposits in the world. So we tend to get a lot of our uranium from Canada.
Woot woot, Canada!
And some of the highest purity ores too.
Yes. Yeah, they got the good stuff.
Okay, so if I took a pickaxe out to my backyard and I started to go, would I find uranium, or is it like way harder than that?
Quite a bit harder than that, I would say.
Yeah.
Okay.
Yeah. Yeah, I know. Oh gosh, I think it's Saskatchewan or Alberta. One of those two provinces actually has a lot of the mines in Canada. So you might want to head over there first and then start digging. But you got to go pretty far down.
Well, we are in Alberta, so okay, perfect. So it's not like Beaker could dig this up when she goes after gophers.
No.
Unlikely?
No.
Unlikely?
Very unlikely.
Okay, all right, good.
She's more likely to just...
we don't want Beaker to get radioactive superpowers. That would be too much Beaker.
No, she already has way too much energy.
Okay, I'm sorry I cut over the person talking there. We have to mine for it. It's in certain places in the world. That's the fuel that's used to heat up steam. So we're basically, instead of burning coal, we're heating up steam. Am I on the right track? Instead of burning coal to heat up steam, we're using the nuclear fuel to heat up steam.
Yep, that's right.
Okay, cool. All right. Okay. So here comes the next question. And again, panel, anybody can answer this. And if you have anything to add, go ahead. The second question that people probably have a lot of, concerns about is nuclear power safe? Because there are countries around the world, like Germany was in the news, they're shutting down a lot of their nuclear power plants. And that may not be because they think it's unsafe. There may be other reasons there, but overarching question that we get a lot is nuclear power safe?
So we are definitely biased, so we'll start by acknowledging that. But the answer generally is yes. Nuclear power is safe. If you're comparing it to like coal or natural gas, it's far more heavily regulated, especially in the US, than either coal plants or natural gas, or a lot of our other power currently, which, because it does, we understand it has the potential for things to go a little bit sideways with nuclear. As you know, there's potentials for explosions with everything else. But it's very heavily regulated in the US. The doses are constantly monitored. The plants are constantly monitored. They have very strict licensing and upkeep. And it's probably one of the most well-regulated industries, let alone power industries. Amanda or Jeremy, you may have something to add to this one.
Yeah, I'll just chime in that partially thanks to this really strict regulatory regime in the US and elsewhere, even including the most notable accidents that people can think of, 3 Mile Island, Chernobyl, and Fukushima, it remains one of the safest sources of power, very, very high up there amongst the safest sources of power if you measure it on a deaths and casualties per unit energy generated basis, which is how we can kind of compare it to these other apples and oranges of different power sources. If you look at its safety track record versus things like coal, wind, solar, it actually is down there very, very near the bottom in terms of the adverse impacts it's had. Coal being a very, very bad contender there. Solar and wind being good, but still having their own issues with construction accidents and things like that.
Oh, right, because those windmills are so tall.
Yeah, and they need maintenance, right? There's always workplace hazards in every single industrial process you're going to have. You're always going to have some accidents. Carries a risk, but best we can do is try to minimize those risks.
Amanda, go ahead.
Yeah, I think the other thing I want to add there is the people that are operating our nuclear plants, you will never find anyone that knows their equipment better than those operators. So in the US, at least, the operators, you have 2 different types of operators. You have reactor operators and senior reactor operators. And it's just a different level of classification, different level of training and whatnot. But at the very least, you're going to be in school for at least 6 months to a year learning just about that plant and absolutely nothing else. And then once you actually get on to your operating shift, you work in a 5-week rotation. So the first 3 weeks are just different shift schedules of operating the plants, right? Because these things are running for 24 hours a day. The 4th week is just training. You're just in the simulator that's on site. So it's, a replica of the control room for that unit. You're going through, regular operation drills. You're going through drills on accident scenarios. What happens if you lose a bunch of water or something breaks that shouldn't be breaking? Like, these people know what they're doing and they know how to handle any adverse situation they're going to face.
This is Discovery Matters, a collection of stories and insights on matters of discovery that advance life sciences.
Brought to you by the people at Cytiva and driven by our curiosity for all things science. And we've actually heard that it's got real health benefits.
One listener told us that she started running faster thanks to listening to us.
So do it for your health or for your curiosity.
Either way, give us a listen and a rating.
Okay. All right. So we're not talking Homer Simpson level of skill level at working at these power plants.
Oh, absolutely not. Homer Simpson he's a cartoon for a reason.
Okay. Thank you. All right. So we're going to hop back and forth between our serious questions and our less serious questions. So, panel, are you ready for the one of the fun questions?
Definitely.
Okay. So this is along the lines of safety, right? Since we were talking about is nuclear power safe. So let's say I'm a very, very rich, billionaire in the United States. Maybe I tried to buy Twitter and it didn't really work for me. I've had a bunch of bad press. And since I'm only a day or two away from being a supervillain anyways, it's the straw that broke the camel's back. Now, let's say somebody went full supervillain. How hard would it be for someone to build a dirty bomb? You know, those ones they talk about in movies where somebody like gets their hands on, I don't even know what they're getting, and they build like quote unquote a dirty bomb. So that's the question for the panel. I've become a supervillain. I want to take my frustrations out on the world.
So I'm going to start on this one because my expertise is in nuclear security. And the answer is that it's harder than you think. Well, it's as hard as you would hope it to be. And so we have lots of different types of radiation detectors set up, especially in places where we know we're going to have fuel, especially in places where we know we're going to have like different sources of radiation. So they're kept fairly secure. For a dirty bomb, as opposed to just making like an atomic bomb, you don't necessarily need uranium, but you do need something radioactive. So the places where you can get something like that could be at a facility like a national lab. A number of grad students, and especially in nuclear engineering, we happen to work through or with national labs, or our universities have their own sources. And then you could also get it through some place like a medical facility that when they have isotopes for different medical treatments, things like that. So off the top of my head, those are probably the four, if you're including the power plants themselves, biggest places where you could actually get the material to do this. National labs, exceptionally difficult because you have to get on site, then you have to get into the building, then you have to get into the room specifically where these things are kept, then you have to know what you're looking for. For universities, you've got a locked door, a second locked door, usually a locked cabinet as well. Plus, you have to know what you're after. Medical facilities are much more carefully guarded as well because their equipment is so expensive, and it's usually for like capitalist purposes as opposed to educational purposes. So that's very well monitored and kept under lock and key. And then we have things set up, even if you're trying to smuggle material like across the country. One of the things that I help do is I set up monitors for cargo containers to make sure that nobody's taking anything through our ports in our, like carrying things in our trucks. Every time you go to an airport, you're also getting scanned for radioactive sources. Just passively scanned. They're not like actively irradiating you, but they're looking to see every time you go through, those metal detectors, they're looking to see, is there anything that radioactive coming off of you? So it's difficult to get your hands on a source that's going to be big enough to do quite a bit of damage, because it's kept under lock and key in so many places.
Okay, so I can't just show up in a van with like the janitor's uniforms on and come in with a garbage can and like take a whole bunch of this stuff out.
Definitely not.
Okay.
Because you're going to need...
I think I saw that, and we'll talk about movies a little later, but I think, yeah, go ahead, Mairead.
I was going to say, you're definitely going to need at least a badge.
Okay.
So you're going to have to forge a badge first, or illegally acquire one just to get on site. There's a lot. It feels very like Ant-Man trying to break into the one place where everything's got to be set up so perfectly. It's kind of how it would have to go, because we do have like guards that are set up in almost all of these places. You do have secondary like identification, like a badge, and some of those badges have access to certain rooms and not other rooms. So we do have a lot going on, because not even just for people stealing these things, but if we don't know where it is, that can also end up being a different problem, and that can be dangerous to not know where our radioactive sources are.
Yep. The only thing I'll add to that answer as well is that even once you get past all of the security, the two things you need for a dirty bomb are an explosive and then the nuclear material. And not just any nuclear material, you need something that's really, really radioactive, because the whole point of the bomb is you're dispersing it. And so if you have a fairly small source, it's going to get dispersed and spread out enough that it's probably not a health hazard anyway. So you need a really, really pure source that's very radioactive, that once you disperse it, it's still a health impact for the people that you're ostensibly dispersing it around. And that presents the additional issue of you're having to, in order to assemble your bomb, you're having to handle extremely, extremely radioactive stuff that even dispersed is dangerous, but then concentrated before you detonate the weapon, it is going to be lethal on the period of like days, right? So the material itself has a built-in defense mechanism against you handling it. And we need very, very, very specialized facilities with lots of shielding and very big safety measures in order to be able to handle this stuff safely as scientists. To try to steal it and transport it in a trash can, you're probably not going to have enough shielding in that trash can to make it last very long. Your days are numbered handling that kind of material with not the proper stuff.
Or you're going to have the heaviest trash can there ever was, because it's just going to be straight up lead.
You're going to have to
trash can.
Yeah, you're going to have to sneak into the national lab with like a tractor or something. And I think that's going to be pretty noticeable.
Okay. So I think I've got my question answered. You either have to be super swole and not care about your life to get this stuff out, or be Ant-Man. So not real likely. Okay.
That's about right.
Okay. All right. Back to our serious questions. And this one is a serious question. I listen to a lot of science podcasts. One of my favorites is The Skeptic's Guide to the Universe. And one of the things they're always talking about, and from doing extra research, is that like nuclear power is the thing that can realistically do the most to help climate change right now, because wind and solar are amazing, but we just don't have the battery capacity to keep wind and solar keeping everybody's lights on right now. So my question to the panel is, as people that are working in nuclear, is that sentiment true? Like, is nuclear power the secret weapon against climate change right now, or part of the solution, or not at all?
Oh, it absolutely is. And if you talk to anyone that, works within nuclear energy in some capacity, I don't think we really consider it our secret weapon, because to us, it makes a lot of sense. So when you look at energy sources, we tend to kind of group them into two different categories: baseload and then intermittent or variable sources. So baseload is that stuff that's always going to be operating. It's going to be providing energy 24 hours a day, 7 days a week, when, as much as it will be able to produce. So that way, we can meet the baseload energy, because we're always going to need some amount of energy, right? And it's pretty constant for a given region. And then you have the intermittent sources. So, our energy demand curve, we call it a duck curve. Someone decided that at some point it looks like a duck when you look at it over a 24-hour period.
Okay.
Because it's kind of like a certain amount, when we're at midnight, it kind of goes down a little bit throughout, or like when you hit like midday, and then it goes up as people like start coming home and, turning on all the appliances in their house and whatnot. So someone decided it looks like a duck. And so, nuclear is great for providing that base load. And then, we can use other variable intermittent sources to kind of fill in those gaps as we need them throughout the day. So we're always going to need a certain amount of energy, and nuclear is just the only clean baseload energy source that we have right now. Because the other baseload energy sources that we typically rely on are coal and natural gas, which are not clean sources.
And panel or Amanda, or what do you mean by clean?
In this case, for clean, I mean it doesn't produce any carbon emissions, right? Or at least it produces a very, very small amount, because every energy source is going to produce some amount when you look at the lifetime of all the construction of the site and raw materials and whatnot. But as we're operating our nuclear power plants, because we are splitting nuclei instead of doing combustion reactions, we don't emit any carbon dioxide or any other carbon emissions into the atmosphere.
Okay, so the second part to this question, and anybody can answer it, is why aren't we just going to nuclear right now? Why?
Are you looking for a podcast where you can get a big dose of hope in just 30 minutes? I'm Soraya Diasi-Kofelt, the host of the podcast Be Convinced, where I share life-changing stories of hope that will encourage and empower you. I'm an Ivy League educated lawyer, a former judge, small business owner, children's author, wife, and mother who's passionate about helping you to overcome challenges and improve your life. Because of my diverse education and life experiences, I bring to you a wide variety of guests who share their heartfelt, life-changing stories of hope to inspire and motivate you. Please join me on this motivational journey and be convinced that there is a better future.
Oh, so this has a number of reasons. And one of the big ones is that as much as we have so much regulation, it's great. But it can also be kind of limiting and expensive. So building a nuclear power plant is expensive, but it's also expensive, to have all the people that have to go through the licensing checks and everything else. So nuclear power it can be slower because they have to build the facilities, and it can definitely be slower because it does take, for our current reactors that we're using, it takes a lot of startup money. And that's one of the things we're working on, things to make that a little bit easier. Small modular reactors, things that don't require so much money up front. But we also have a hard time with finding places to put nuclear power plants because a lot of people don't understand the full repercussions of nuclear or the lack thereof. So we have a lot of not in my backyard type mentalities when it comes to trying to find somewhere to put a new nuclear power plant. And that can also be difficult to kind of get around and get over is trying to make sure that you have the public on your side when you're trying to create a new power plant. So both of those things kind of really limit how quickly we can put up new power plants. There's definitely other things, and Amanda and Jeremy, I hope you'll chime in, but those are the two that originally that come to mind first for me.
Yeah, I think to add on to why it's so slow, right now we're working on building 2 new nuclear plants in southern Georgia. Those are the first plants that we're building in the US since like the 1990s. So we've lost so much knowledge and experience within our industry of just how do you build these? And so we're really seeing it play out down in Georgia. Unfortunately, that those plants were supposed to be online in like 2019, and we think they'll be online next year, I think. So it's hard. They're monstrosities of cement and pipes and whatnot. And so when you don't have anyone that has an experience on how to build it's really hard.
Yeah, and I'll just add a little bit onto that this is something that's seen kind of across the board, especially in the United States, but also in other places too, not just with nuclear, but other large, what we consider mega construction projects. The cost overruns and our ability to build large things like massive rail infrastructure or huge bridges and things like that has generally, it's gotten a lot harder. It's gotten a lot more expensive in this country. Grown much faster than inflation. So that's a challenge that building these huge nuclear plants presents to that, and why microreactors might help with that. And then additionally, just going back to what Amanda said about how nuclear is useful for certain things like providing baseload energy. Unfortunately, once you do have a nuclear power plant online, it is providing baseload energy. The way our current energy market is set up, it is not really set up to incentivize baseload energy or to value baseload energy. Nuclear doesn't get special monetary bonuses because they're providing this baseload energy that's reliable. We don't really pay for reliability in this country. We just pay for every kilowatt hour that's generated. And so that additional benefit that nuclear has isn't really built into the value structure, and it loses out in that regard.
Mm.
I think a final thing to consider here is also to an extent politics, right? So power plants and energy generation are really decided on local levels. Like we don't have our federal government saying, okay, we need a power plant here, we need one there. It's all on local levels of region or state or even sometimes individual municipalities. And actually we see in a number of states, I think right now the number is 12 different states have moratoriums, legal moratoriums on building new nuclear plants. And kind of ironically, Illinois, which has the most nuclear reactors of any state in the US, we have a moratorium right now. We're working on getting it repealed, but legally we can't build any new plants.
Somebody used, somebody had some anti-nuclear political platform, got voted in, and then kind of like that's the thing. Is that where you're going with that, Amanda?
To an extent, maybe in other states what it is, that's, how they got their moratoriums. West Virginia pretty recently repealed their moratorium. But they're a huge coal industry. So I think they're really just trying to promote their own, internal state industry. In Illinois, actually, my understanding is, we built all these nuclear power plants, and then we were kind of like, okay, let's hold off for a little bit until the federal government solves comes up with a solution for nuclear waste that is not just keeping it on site. So we were kind of hoping that federal government would come up with an answer on that one, and yeah, we're still here.
Okay. All right. So the next question is a fun one, and anybody can answer in any order. And this is about movies. So in Hollywood movies all of the time, in science fiction movies or, near future movies, or even movies about now, nuclear power is, it's shown on screen. And my question to the panel is there a movie that you've watched that you're like, whoa, that is so wrong? We'll start with that. So is there a movie that jumps out at you that, boy, they got that wrong, movie or TV show that got that's super wrong about nuclear power, nuclear energy?
So I feel like you almost never see nuclear power in movies, it's always, here's a nuclear weapon. It's rarely like, we're going to blow up this power plant. In movies, it's always some like very James Bond, like, we've got two halves of a plutonium sphere and we're going to blow up this bomb. It's almost never just like the power and the power plant itself. Like, it's always like a U.S. Like, it's almost always a U.S. cruise missile type thing. So there are definitely a lot of things that could be better about how nuclear is portrayed. One of which could be just portraying nuclear energy as like a thing.
Like the main character works at a nuclear plant and it's not like that's just their job. And then they just like, it's just part of the TV show. It has nothing to do with what's going on. It's just that their job there. Oh yeah, I work at a nuclear power plant.
Yeah, it's exactly like, it's, normal people do these jobs. It's nothing that's completely crazy. I mean, normal people do these jobs. And unless you're looking at like the new 3 Mile Island documentary or the Chernobyl documentary or something like that, you don't tend to see nuclear energy. Correct me if I'm wrong, other panel speakers, but it's almost always some like, we've got two halves of a giant plutonium sphere and we're about to steal one or the other.
Yeah, I agree with you on that one, right? I think the other thing we see a lot that's nuclear related in pop culture as a whole, but also in movies, is like, oh, I was exposed to a radioactive material, so now I have all these different mutations. I think that's another thing we kind of see a lot.
Yeah, I'm racking my brain, and the one I could think of where nuclear power is featured, and this is kind of on the plasma side, is Back to the Future, the Mr. Fusion fusion energy site, and that's not quite going to ever be how it works. I don't think. I think in there they're portraying that you can just take any random trash, fuse it, and you're going to get energy out of that. And that's not strictly true. It's hard enough to fuse hydrogen, even in some future situation where they're trying to throw like soda cans, aluminum cans into there or something. You really can't just take any two elements, fuse them, and get energy out of it. Sometimes when you fuse elements together, you actually lose energy out of the deal. That's how stars die. So that's the one I could think of off the top of my head.
Doesn't the movie start out with him like stealing plutonium from a lab, or is that a different one? I thought that's how Back to the Future starts.
No, Doc Brown definitely hires Libyan terrorists to go get the plutonium.
Okay. I knew there was plutonium somewhere in that movie, but I didn't remember he actually uses it anywhere. All right, cool. I'm not completely unknowing in pop culture.
I just saw like a bunch of plutonium, and by a bunch I mean extremely small quantities of plutonium metal, like 2 weeks ago when I was at a different national lab, and I have to say, it's not nearly as cool as they make it look in the movie. Half the time you see it, it's like some like pinkish powder oxide. They're like making it into a metal in small quantities. It's not nearly as fun as you think it's gonna be. It's a little bit disappointing, actually.
Now, the most disappointing thing is, I do believe in Back to the Future 2, they travel to the future to 2015, which was like 7 years ago, and we still don't have fusion. And we'll get to that a little later. But that's also disappointing for me.
We also don't have like the hoverboards or whatever they had in that movie.
Oh yeah, that's true. That's even more disappointing.
Yeah, that's what I'm probably more sad about.
Okay, so the second part of the question. Oh, anything else from the panel about movie myths before we move on?
The China syndrome's not going to happen.
What's that? What's the? I'm not familiar. I'm sorry.
So, the China syndrome is a movie from the 70s, and it came out 1979. And it came out like just before 3 Mile Island, right, Amanda?
Yeah, that's how I remember it came out in 1979.
Yeah. I think it came out like 6 months before Through My Island happened here in the US. And the concept of the movie was that there was a nuclear reactor and there was a big meltdown and it melted. The core was going to melt straight through the Earth's crust, through the center of the Earth, and go all the way to China from the US. So, like, first of all, there's so many things wrong with that. One, geographically, that's not how that works. Two, there's no way that it would melt through into the core of the Earth and would be so much hotter than the core of the Earth, it would just keep going out to the other side of the planet. Two, it just wouldn't get that far. That's not how like the melting works. It's not going to go down like miles underground when a core is like melting down. Basically, it's just turning into like nuclear hot lava melt. And it just doesn't melt like vast quantities of ground. And it came out at such an exceptionally poor time in light of the fact that, you know, Through My Island happened like less than 6 months later, that it just stoked so much fear and concern because this movie had come out and it was, you know, it was so the end of the world and it was such a big deal. And then the event, like, people were like, oh my gosh, is like this movie, is the China Syndrome going to actually happen there in Pennsylvania? Like, what? No, it wasn't going to. It's not going to. But
Okay, so sorry, but I actually really want to talk about that movie myself because, like, that's like I think what everyone remembers about that movie the most because that's what has like continued to, you know, be like that is like the single clip of the movie that comes out that like people show the most is like that single scientist being like, this is what the China Syndrome is, blah blah blah. But like the whole like actual premise of the movie, I think, is more about like because it's about these workers that are on a power plant, right, nuclear plant, and it's like this one guy thinks he's going crazy because he thought that there was like some tremor in the plant, but then everyone else is like, no, you're fine, like nothing happened, the plant is perfectly safe. And then like at the very end of the movie, some like pipe ends up breaking and a lot of not good stuff happens. So like there's a lot more to that story than just like, oh, a core is melting. Like that doesn't actually happen in the movie. It was like, oh, this could have happened or something like that. So I really encourage everyone to watch that for themselves because I think people take away from that movie, like, or like their perception of that movie is just that one single scene when I think there's so many more things that go on. I think it speaks more to things like human factors and operations and trainings and the workers that are at a power plant is like kind of my bigger takeaway from that movie than like, oh, like, you know, this one myth has like, continued to go on third time from that movie. So.
Kind of like if you watch Chernobyl, the documentary, you can clearly see it was like bureaucratic incompetence, cover up, all of that made things way, way, way worse. And it's not necessarily about the meltdown potentially.
Yeah. Yeah. I think it's a little more akin to that, but I definitely encourage everyone to watch China Syndrome for themselves. And I'll let you see if you agree more with me or Mairead on that one.
Okay. Jeremy, have you seen that movie?
I haven't actually. That's one of the famous nuclear movies that I actually haven't sat down and watched yet, and I really need to.
That's not like on the syllabus in first year to be a nuclear person. Like it's not like, okay, in order to pass this class, you're all gonna watch the China Syndrome. No? Okay.
No, it's not. But we all do joke about sitting down and watching it together pretty frequently. It just really? Hasn't happened yet. Yeah, no, we do. It's one of the big ones.
Oh my goodness. Okay. Interesting. Now, on the flip side, is there a movie that gets nuclear power right?
You already said it, and it's not a movie, but the series, the Chernobyl series actually does a pretty good job. I've guest lectured in a couple of like introductory energy sources classes, and I actually gave a guest lecture on the Chernobyl series because it does such a good job of covering that accident. in a layman's sense. So I really like the series. There are a couple of embellishments that they make throughout, but overall, especially in the courtroom scene, if you've seen it, they go over kind of a play-by-play of what happened in the accident scenario, and it's pretty accurate.
Yeah, I would agree. I think the one thing that they don't get right in that series, and this may be included just because that was, possibly like the understanding of people's perception of, or like knowledge of radiation at the time. But there's a pretty common thing of like each person that, receives a dose of radiation during the series, then everyone else is like, oh, we have to stay away. Like they are now radioactive themselves. Like that part is not correct.
Yes.
If you receive a dose, you are not radioactive and you cannot give a substantial dose to someone else. But yeah, definitely all like the reactor physics that they talk about in the court scene, that is spot on.
Yes, radiation sickness is definitely not contagious. The only way they could be dangerous is if they actually had some material still on their clothes. But at that point, they had changed clothes.
So I have a question. What about Marie Curie's bones? Is that a myth that her bones are radioactive because she worked with radioactive materials so much?
Well, she was working with... All right, correct me if I'm wrong here, because I believe she was working with strontium-90 at one point. And
maybe she worked a lot with plutonium, uranium, or not plutonium, polonium, uranium, and radium. I think the three main ones she did.
So the reason why I brought up strontium-90 is because strontium-90 is absorbed in your bones.
Okay.
So that was the only thing that I could think of why that might be real, is because, how your bones take up, they have calcium, and amongst other things. Well, it'll also take up strontium. And so strontium-90 is a fission product. And so that's one of the things where if you were to ingest it, or inhale it, like, that would be the only thing that I can think of where you'd end up with like actually radioactive bones. Oh man, it's too bad Emory isn't here. One of their specialties is in health physics, and they would know better than I would. But that's the only isotope I can think of. It's kind of like when you have thyroid cancer, they give you like radioactive iodine. And so that goes all to your thyroid because that's just sort of where iodine collects. Strontium just kind of collects in your bones. Don't inhale or ingest vast quantities of it. We don't recommend that. It's not like it's commonly found in nature either. You'd have to really kind of go out of your way to try to do that.
Kind of like Marie Curie. She definitely went out of her way.
Yeah. But as I said, off the top of my head, I can't remember whether she was working directly with strontium-90, but that's the only isotope that I can think of that is very much known to be uptaken into your bones. I'd have to look it up again.
Well, I just pulled up the periodic table. Radium is also a group 2 element, so it'll probably be taken up by bones too.
Yeah, radium definitely is the other concern. I think she won the Nobel Prize for discovering radium. So I think that's probably the primary concern.
Yeah. So to explain some of the science I'm thinking about right now. So group 2 elements on periodic table, so 2 valence electrons. So another notable group 2 element there is calcium. So your bones will naturally try to, take in calcium. It helps make them stronger. And elements that are in the same group on the periodic table will behave similarly, right? So radium and strontium will behave similar to calcium. So your bones will try to absorb those as well if they're in your body.
Well, I only know about burning strontium in chemistry demonstrations because it burns like a beautiful reddy pink for the children. It's not radioactive, though, I hope.
Strontium? There are some radioactive isotopes, like
okay.
strontium-90, like Mairead said. Yeah.
Oh, okay, yeah.
But
no,
I'm sure whatever we're burning is is a stable isotope.
Yeah, it's strontium nitrate. It's stable. Yeah. Okay. Well, thanks for that. I have like a bunch of follow-up questions, like even from radium. I went down this deep dive on the internet. There's the radium girls in the States that were using radium paint to make the dials glow. And then basically they got radioactive, their faces got destroyed from it.
Yeah.
Like that's another thing that goes with radium. I think like Mairead, you were talking about that too.
That's really tragic.
Yeah. So like all of this stuff's super dangerous, but, anyways, let's go back to the more serious questions. And this one's more up Jeremy's alley. So Jeremy's time to shine. And that's, what the heck is nuclear plasma?
Nuclear plasma. Okay. So, plasma generally is, we consider it the fourth state of matter. So, you take a solid, heat it up, it becomes a liquid. Liquid, heat it up, it becomes a gas. If you further heat up a gas, and that's one way you can make a plasma. If you run an electric current through a gas, you can also make a plasma. And physically, what's happening there is now you've added so much energy that not only are you making the atoms so that they zip around pretty much independently of each other, but you're actually adding enough energy to knock one or two or more electrons off of the atom. So it now becomes charged. So you get these positively charged ions, which are the atoms minus a couple of electrons. And then you get the negatively charged electrons that are zipping around. And how this relates to nuclear science is that the most famous plasma that we're all familiar with in our daily lives is actually the sun. You might have heard it described as a big burning ball of gas. More accurately, it's described as a big fusing ball of plasma. It's in the plasma state, and it's not actually burning. That would be combustion, reacting something with oxygen to make new molecules. If it were providing its energy by combustion, it would have burned out long ago. There's not enough gas there to burn in order to produce as much energy, and for it to produce as much energy as it has been. It actually needs to fuse. So take two lighter elements and fuse them together, combine them together into a heavier element, the opposite of what we're doing with fission within the nuclear power plants we've been talking about so far. But it still produces energy. And what the sun does is it takes specifically hydrogen and fuses it together eventually into helium. And eventually it will start fusing that helium together into heavier and heavier elements until it gets to iron. Iron is the most stable element on the periodic table. If you try to fuse iron, you stop getting energy out of it. You actually start putting energy in. And at that point, the sun starts to lose energy until it collapses in on itself. That was kind of a winding answer, but
no, Jeremy, yeah. That's interesting. You said that. I was talking to on one of these spaces an astrophysicist, and that she mentioned that iron is the last element that stars can make. And I was like, what the heck? Well, what about all of the other elements? And then she said that they're made from what they are pretty sure is from these other stars called neutron stars smashing into each other.
Yes, and some of the heavier elements can come from supernova as well.
Oh, right. Okay. Explosions. Yeah, gotcha.
Yeah, that last spectacular moment when the star's gravity starts to crush it in super hard. In that last moment, it can fuse a lot of those heavier elements together. It actually loses some of the energy in doing so. But at that point, it's just crashing into itself so hard anyway that it doesn't matter. And then it explodes outwards. And so that's actually how we know that we ourselves are made of stardust currently, is that we have some of these heavier elements around here on Earth. We have uranium, we have thorium, we have these things that are way past iron on the periodic table. And so they couldn't have come from like a first generation. They have to come from these huge supernova explosions.
Nice. Now, the question from me to the whole panel is, and maybe Jeremy, you can keep talking about this. How does nuclear plasma, factor into what Amanda's studying or Mairead's studying, or like us in general? How, aside from the sun? I mean, the sun's kind of important. Don't get me wrong. So go ahead.
So There are some crossovers in the energy sector. So obviously we can build solar panels and get some energy from the sun that way. But really, long term, it might be interesting for us to be able to try to replicate that process here on Earth. So this would be the inverse of what Amanda and Mairead are doing with fission. But if we were able to take some of the hydrogen we have here on Earth and fuse it together, we could get energy that way, and we could potentially build power plants that way. The benefit there being that uranium, while it's very energy dense and we have quite a bit of it on the Earth, it's by no means the most abundant element on Earth. We actually have a lot more of hydrogen in the form of water. So if we could use hydrogen as a fuel source, that would be super, super handy. But even outside of the like fusion energy sector, there are some crossovers between fusion and the type of research that Amanda and Mairead are doing, in that fusion can be used as a neutron source. By fusing things together, we can produce neutrons. Those neutrons can be used for radiation imaging. There are lots of kind of niche applications like that. And I don't know if Amanda or Mairead want to jump in on that.
I'd love to jump in on DT generators, if that's cool. So I do almost all my work is in neutron imaging and neutron detection. I've done some other like gamma detection or different charged particles, but I mostly do neutrons. I like them. They're my favorites. So with neutron detection, there's two different ways that we can do it. One is through active interrogation, and one is more of a passive interrogation. And this all relates back to security pretty well, and trying to find things that are either giving off neutrons, or whether we need to bombard something with neutrons to make it react so that we can find something. So I was just in California at a different national lab. Typically, I work at Oak Ridge National Lab, but I was out in California working on a project. And their thing is, if they take one of these fusion generators and they bombard a whole cargo container with all of these neutrons that come out of this fusion process, can they detect what is in that cargo container? And that's basically saying that if you have something that shouldn't be there, the things that we were using for examples were something that's going to be, a neutron emitter. Like if you had uranium in the truck and you bombarded it with neutrons, you would get some smaller fissions, and you'd be able to see the results of that from outside of the cargo container itself. But you can also do this but you can also be looking for things like cocaine or explosives. And so it's not just nuclear material that we're using this for, and we're using these DT generators for. We're saying if we can use these neutrons to irradiate, we can look for lots of different things. And so DT generators, which are basically teeny tiny fusion machines, super cool, they are so incredibly useful and helpful for developing new systems of radiation detection and new systems for scanning. They're super helpful for different experiments when you're testing things. So nuclear little teeny tiny fusion generators are so awesome, but it's really hard to turn them into full-blown power plants. And that everything after that is a Jeremy question. But teeny tiny fusion machines, I love them.
I think the other fun application of nuclear plasmas that I'm surprised Jeremy didn't mention, we use plasmas to make semiconductors for things like computers and electronics. So I literally would not be able to do my research, because I do all modeling and simulation on computers, but literally not be able to do it if we didn't have plasmas to make those semiconductors.
Yes, that's very true. I was focusing on like the pure nuclear science, but also plasmas can be used for making lots of really cool things.
I love it. So from the sun, we can scan cargo containers for like, contraband bacon or something like that in the future.
Absolutely.
Got it.
I'll tell Beaker.
Okay.
She can be there to claim all the bacon.
Okay, sounds good. I love it. Okay, thanks. All right, let's move to one of our fun questions. And this one is things that you, in general, in the future, if you could think of one or two things, what are you most excited about with nuclear energy, nuclear power / nuclear science?
Space.
Explain.
So we only have a certain number of radiation detection classes that we offer at the University of Tennessee, and they're great. But we also have a space science institute, and with Oak Ridge National Lab right here, we do a ton of space nuclear research. So I have now taken so many classes in space nuclear applications, which come in kind of two forms. One of which is called a radioisotope thermal generator. And that is basically a small heater where the heat source is a decaying isotope. And you can attach that to a little generator and it will change that heat over into electricity. And you can use that for very long-term space missions to actually power a lot of your equipment, which is really cool. And that's what the current Mars rover is doing. They have a whole bunch of these little pellets of plutonium-238, which has a half-life of 88.7 years, and which means that after 88.7 years, only half of it will be left. But that's enough decays that it does produce a good amount of heat. And it will keep producing this heat for such a long time because it has this half-life. And so we connect this to different little generators, and we actually make small electricity batteries, nuclear little batteries, that we can put on the Mars rover. We can use it to power a whole bunch of things that we're sending into space. All of our equipment, the further you get from the sun, you can't really use solar panels anymore to try to actually power all of your space shuttle equipment or your, rover equipment or everything. So we can use radioactive sources to actually create power. And so the other space thing is nuclear powered rockets. And so nuclear powered rockets are really interesting. And not only do they tend to produce enough power to generally power whatever space shuttle it's attached to, but because there's so much more energy released from fission than from combustion, if we can actually do fissions in space, we can eject hydrogen out the back of the rocket that we create, and we can move so much faster than we could with just with our standard combustion, which is great because it means that we might be able to reasonably get people to Mars if we are able to get to Mars so much faster. Because right now it takes so long. It's it's like 2 years and 7 months or something.
Yeah, it's like 6 to 8 months there, 6 to 8 months there, and then you gotta wait a bit for it to be a perfect thing to get back. Yeah, it's a deal.
Yeah. So if we can get there faster by using nuclear fission and nuclear rockets, that would be a huge benefit. So those are my two, or space nuclear is my favorite application of nuclear. And I think it's the coolest thing. It's the thing that I'm the most excited about. And it's so cool. It's amazing.
I think my answer has to be what we were just talking about with fusion. It's what got me into the nuclear field. It was my initial interest here. I've since shifted gears and my focus for my research, but fusion energy has the promise to be a extremely efficient energy source with a pretty much inexhaustible supply of fuel. We have enough hydrogen here on Earth to supply fusion reactors for not even measured in the thousands of years, but millions of years, even with growing energy demands. Something like the first inch of water off the top of Lake Michigan would be enough to power the United States for something like the next 10,000 years. It's just a ludicrously dense fuel source, and also, fortunately, the most abundant element in the universe. So if we could switch our fuel use to that, our energy source to that, we wouldn't have to worry about finding more fuel for a very, very, very long time. The challenge is to achieving the ability to take a miniature sun and stick it in a bottle here on Earth and then actually get energy out of that are huge. It's just an insane project. But if we could make it work, it would be incredible.
I think for me, the thing I'm most excited about is just in general new reactors. I mentioned earlier that we haven't really built a whole lot of reactors, or really any, since the 1990s. And so, if we can get more reactors, help address climate change, while still providing the energy that we need for our daily lives, I think that's really exciting. And right now, Marie kind of mentioned it earlier, but we have some new reactor designs that some of them are really different from what we have right now, actually, powering the US. And so just building new technology is always really exciting. And, some of these partnerships, or some of these reactor builds are through the Department of Energy, the Advanced Reactor Demonstration Program. Some of them are with various municipalities. Some of them are actually with universities, like the University of Illinois right now is looking to build a new reactor on campus. So, making sure that our university has the state-of-the-art technology for our students to do, get hands-on training with, do research with. It's just the idea of just building new technology, and while also still meeting climate change, is just really exciting for me.
So we had a couple answers from outer space, and then we had one for here on Earth. So it sounds like we're looking to the stars and also looking into our backyard, which is kind of cool. Panel, are you okay to take some questions from folks? Can you stick around for another 10 minutes or so?
Sure, let's do it.
Yeah. I purposely left out a whole bunch of questions that maybe some people in the audience would have. There's not enough time actually for me to interview and answer all of the questions that there are possibly there. We have an amazing panel that have varying, they have different areas of expertise. So now's the time, if you are part of the space, or if you're on Clubhouse, or if you're on Wisdom, if you'd like to ask a question of our panel, you can request to come up to ask. Now, Chris is going to help me get people up. We are only going to take people on stage that we have a general idea who you are. So if you have a locked account, or we do our back end on you and you're kind of, it looks like you've been tweeting some sketchy stuff, you may not get to ask your question. Also, if you're shy, you can DM me and I can ask the question to the panel. So we can move on to questions. Chris, did you bring somebody up? I was talking and checking my DMs.
I brought Liz up.
Okay, perfect. Go ahead, Liz.
Well, thank you for not thinking I'm sketchy.
Well,
I know. Excuse me, I was going to chime in because you guys mentioned something earlier. Back in 1998, so it's been a hot minute, I actually had thyroid cancer. And I was getting treatment and stuff at Hopkins. And one of the treatments, they had me do the radioactive iodine. You go into the room and they have this lead-looking shaker, and they're full PPE. And they're like, here, swallow this. I'm like, you want me to do what? And then I had to stay in a room behind lead shields for an entire weekend while it did whatever. And then they told my family that for a month afterwards, because I was only like 15, 16 at the time, couldn't share silverware, couldn't share anything that could possibly exchange body fluids because they might have then been at risk. And then, of course, ever since then, I've had to take loads of calcium every day because starting around then, I got the osteopenia. So nuclear stuff is great, but I just wanted to kind of share that because it was anecdotal for what you guys were talking about.
Yeah, definitely appreciate you sharing that. So actually, my PI at Oak Ridge, he also had thyroid cancer and he received radioactive iodine treatments. But he's a nuclear physicist and a geek in the most loving way possible. I say that. So at one point, all the other guys in the group, they set up a bunch of detectors around him and they measured him for like quite a while. And then they reconstructed it. So he has like images of him sitting in a chair where they reconstructed him with his radioactive iodine source and they imaged him so they can see exactly where the radiation is, how much it is. They've got some crazy images from his radioactive iodine treatment. Because apparently they were all sitting around and didn't have better things to do with time. And it was fun.
Anything else from our panel before we move to the next question? Okay, we'll go to...
Sure.
Go ahead, Dr. M.
Yes, I'm really bummed. It's a great space. I'm really bummed I missed the beginning of it. I was hosting another. So if you've covered this, we can move on and I'll just catch it in the recording. But my question is about power generation from nuclear facilities. I'm someone who's not really aware of the nuclear space. My question is, I imagine that at some level, events like Chernobyl would cause the society and public overall to kind of push back against accelerating generation of power from nuclear energy. My question is, is that the case? Are we building many more nuclear facilities? And basically, if anyone has any thoughts on that, I imagine, those reactors are very decades old. I imagine design of 2020 to begin building reactors today would be likely a lot safer. If anyone has anything on this question, it seems to me like we should be building a heck of a lot more nuclear power plants. Are we doing that? Are there concerns that I'm not aware of?
No, this is a great question. Thank you. So as far as new nuclear builds going on, right now in the United States, we have 2 new reactors under construction in Georgia. And that's it. Other parts of the world are building more reactors. China is working on building a lot. Russia, I think, is building some. South Korea, I think, has just confirmed that they're going to try and start building more, and they're also partnering with other countries. I think South Korea actually helped, was it the UAE, get their new reactors online? So depending on which part of the world you're looking at, there are definitely a lot of new nuclear plants under construction and starting to operate right now. The US isn't a big part of that, although we do have those 2 units. And then we are looking at, late 2020s, maybe early 2030s or so, starting to build some new ones as we start to fully develop a lot of these new designs that are smaller in nature. So, right now, a lot of our power plants produce around a gigawatt of power, so 1,000 megawatts. A lot of these newer designs range anywhere between 5 and a couple hundred megawatts. So they're a little more flexible on where you can put them depending on the power needs of a specific area. So there's various reasons for why, certain countries and governments decide to build nuclear. There are certain reasons why they decide not to. Right now, Germany is in the process of trying to shut down all of the plants. So it's a thing that, a lot of countries disagree on for sure.
Thank you so much. I appreciate that.
Jeremy Murray, do you have anything to add to that question?
I think we did talk. There were a lot of questions in that question, and there were some of the things we'd kind of touched on is we had discussed why we aren't seeing much in the way of nuclear being built, from politics, the financial burden, and so that's definitely one part of it. Public opinion and citing concerns are always going to be difficult, especially here in the U.S. We have a lot of, we've got a lot of people, we've got a lot of opinions. We definitely struggle with trying to find places where we can have consent-based citing. So we have like the cooperation of the communities as well. And we'd love to say that if we were just educating people more, then they'd all come around to our point of view. But it's not always that simple. So we are really sort of pushing for consent-based citing where the community is involved and we reach out to the community and try to make sure that they're doing, when they're putting these nuclear power plants in, it's not causing a severe amount of undue stress on the people who live there. And it's not going, but it's difficult, right? Because we are fighting up against a lot of these things like the Chernobyl, just the stereotypes from some of the movies, some of the accidents, and that, they don't help. And we all know they don't help. So there's definitely a lot that we have to work with, but it's far easier to really do some of these nuclear power plants when you can actually get the communities in support of having them. They do bring a lot of jobs. They bring a lot of people to the area. And so they're not a bad thing, but it makes everything so much easier when we're able to actually talk to the local and state government of wherever we want to put a power plant, and be able to communicate with those people more effectively.
Can I ask a follow-up on that exactly?
Sure.
Yeah, imagine you were testifying in Congress or in front of one of these state or local legislative bodies or body that had to give permission for doing this. So you have to really dumb it down, is what I'm saying. What would be your argument? What would be the most powerful, most cogent, most persuasive, most logical argument that you could give, the structure of the argument, not the whole argument necessarily, but what would you say that would be most convincing to get the people to actually come around to being more accepting of a nuclear power plant in their midst? But you got to really dumb it down. This is a real challenge now.
Yeah. So fortunately, this is one of those things that the nuclear industry has been getting a lot better at helping to hire people who can actually communicate these things well. So we hire lawyers, and they're great at this. But me, personally, I'm probably going to go about this in what I would think that the argument would be, and I don't know if that's going to be exactly correct as to where I'm going to place the emphasis, but I think one of the more powerful arguments here is going to be the number of well-paying jobs that it does bring to an area. That's always something that at least local governments are going to be particularly invested in, is having well-paying new jobs coming into an area to try to help develop that. There's a number of economic things that can be very helpful for nuclear. And that's probably the basis of what I'd
What
use.
would you do to? I mean, I can see them coming back at you and saying, "Well, yeah, but if you're going to blow us all up, who the hell cares about jobs?" So, what would you do to reassure them about the safety issue, which, of course, is I'm sure, the overriding, maybe only issue.
Right.
Go ahead, Jeremy.
So I think something that I might do is, and Amanda and I have seen a little bit of this in the past couple of years in the arguments to keep the plants that we have in Illinois open, is that some of the best advocates for nuclear power on a layman's sense is the people who actually live in the communities where our nuclear power plants are currently sited. Lots of people testified from the areas where the plants were going to close, not people associated with the plants, but just members of the community. And they had very, very good things to say about the positive impact that the plants had on their community financially, but also on the fact that they felt like they learned a lot from the plants being in their communities. They learned a lot from the safety because plants are quite communicative of any issues that arise, and what threats they pose and how safe they are to their local communities. So I think that one strategy might be to get people, just ordinary folks who live in the towns near these power plants, get them in front of communities where we might want to build these power plants and have them talk about the benefits that they've seen from their perspective, rather than what we see from our perspective as scientists. That might just be one idea.
Interesting.
Right.
George.
Yeah. Go ahead.
George, to answer your question about, with regards to, threats of, an accident happening at a plant, so something like that, you kind of have to have a mix, and this is in general as well, have to have a mix of putting in like objective facts, but then also mixing it with some amount of emotion, right? So when we're talking about safety in nuclear power plants, we have been operating nuclear power plants in the United States since 1957. There is one incident that people know of. And yes, everyone knows about it, but that's really like the one incident that has happened in all of our operating experience. How many times has there been an accident at a coal plant or a natural gas plant? And we don't take notice to it as much because it's so much more common. It's just more part of our daily life that we don't really notice it as much. Another thing is, my hometown was more based on coal. We had a nuclear power plant like an hour or two away, but a lot of our energy came from coal plants. And I still have this mental image of sometime when I was in high school, there was an accident at the coal plant. And there were a couple operators or workers that unfortunately died, and they were burned alive because of just how a coal plant operates. You have all the fire, you have really hot fire, and just having that mental image that has really stuck with me since, again, this happened when I was in high school. So I would not want coal in my community because that's so much more of a regular occurrence than whatever could happen at a nuclear power plant.
How many people have actually died in nuclear power accidents in the United States or around the world, and how many in coal are related?
In the United States, because of accidents at nuclear power plants, 0 people have died.
That's what I thought.
Right. There have been some deaths related to other things from operations, but not because of accidents or radiation releases.
Right.
No deaths due to the fission process, but like somebody's putting a light bulb in and their ladder falls or something like that.
Right. Well,
Like that.
They run their vehicle into a wall there. Right. Yeah. Exactly.
Yep.
Yeah.
That's very persuasive. I used to windsurf in the warm water that came off of Indian Point, and I know a lot about this stuff. And I think I'm fairly rational, but and my wife is too. And we were saying, geez, what the hell are you doing? You're going to glow in the dark. So even if, even with knowledge, it's kind of scary. But the water in the Hudson River was pretty warm around the plant, and it was fun to windsurf there. But I fell a lot.
Yeah. I was just swimming a couple weeks ago at the Clinton power plant here. They have a lake, and it's the same kind of situation. It's naturally warm,
Nice
and it's
and
a little
warm, right? Yeah.
Yep, it's nice and warm, and it's a little bit odd. Yeah, it takes it's hard to wrap your head around this stuff because it's a lot of stuff that you can't see.
Who knows what kind of mutant fish are down there, right?
Exactly.
Yeah, I think that has to be really, repeated to these people, that it just these fantasies and fears just totally fly in the face of reality, and all these oil plants and coal plants and other kinds of plants are just gigantic hazards and gigantic accidents waiting to happen.
Yeah, I agree, George. It would be a shame if, as a society, we are holding ourselves back from further developing this technology just because of,
Mythology.
irrational fears that somebody
Right.
might have from something that happened in a reactor but when they were building it, the design was already many years old, and that was many decades ago.
But they need people like you guys talking about it rather than lawyers. I mean, a lawyer is just a paid mouthpiece and a paid advocate. You guys know something. So I'd love to see more. I'd love to see more from actual scientists who are evidence based and have data to show. Now, not everybody's, persuaded by data, obviously, but that's all we got.
Yeah, I'm so happy that these three amazing scientists came to talk because it's part of science communication. So Amanda, Mairead, and Jeremy, thanks so much. Do you have time to take one more question?
Yeah, I'm happy to stick around.
You guys are rock stars. Thank you so much. Peaceful Warrior, your hand is up. Go ahead.
Thank you very much. I'm a Dr. George Groupie, so I'm following them around. Anyway.
Thank you.
Thank you so much, everybody. I just have two quick questions. The first one is, could you define or what a rad is? And it's my understanding that rad is no longer used vernacular.
Yes, that's true. So rad is the amount of energy deposited in a certain mass that comes from radiation. So it's the amount of energy that would get actually put into something. So we typically, when we're talking about rads, we're looking at more realistically now, we're looking at joules, the amount of energy per kilogram. Those are the kind of units that we tend to talk about, is how much energy gets deposited per kilogram of mass. And so rads was one of the ways that we would measure that. It was one of the units.
Okay, yeah, because I was talking in terms of nuclear medicine, in terms of radiation therapy. And
yeah, so we don't typically...
you can only take so many per day, per week.
Yeah, so if you're familiar with, different types of gamma knife, they will tend to do things in grays now, which is defined as joule per kilogram as opposed to rads. And generally, especially for things like prostate cancer, they'll tend to do about 2 grays per day. And then they need a total of something like 70 grays total for the treatment. And so it's just the amount of energy that they're depositing in the tumor for prostate cancer.
Got it.
Or for whatever other type of cancer.
Got it. Thank you so much. Just one other quick question. The CERN, I think I'm getting this right, CERN Hadron Collider that was just took off again July 5th, I think it was. Does that have any impact on our nuclear power? The the Higgs boson and all that?
So my understanding is that CERN does a lot of fundamental physics research, but the Higgs boson and some of the other stuff they're looking at, that's on an even smaller scale than like the neutrons and protons and electrons that we typically work with. So, they're kind of doing a lot of research on just like, how does the universe operate? What are the, fundamental components to the universe? I think, day-to-day operations of a nuclear power plant aren't really, affected by the science that they're doing there, because it's just on such a smaller scale physically.
We tend to say that stuff like that is still important, especially to national labs. More
not
so
all saying
for,
it's not important.
Oh yeah, just for the continuity of knowledge. That's kind of the key phrase that they use for lots of fundamental physics work, is continuity of knowledge, more so than the direct impact that it's going to have on our work specifically.
And just to tie that in, if you were to rewind 120 years ago, the stuff that fuels our fission reactions today would have been considered basic science back then. I mean, it took until the 30s for people to really start to consider it as a potential source of energy, right? So who's to say it won't become something valuable in the future? We don't know. That's why we research it. But yeah, it's not currently applicable to what we do.
Got it. Thank you very much.
So you guys aren't going to be using pentaquarks and quadraquarks anytime soon?
I don't even know what that is.
Yeah, exactly.
Yeah, that's a no for me.
That's the two new particles that CERN found the last couple weeks ago. I was gonna do it. I was gonna do it as a story, and I was like, nobody cares about this. It's so complicated, and I squashed it. So yeah.
When they started telling me about top quarks and up quarks and down quarks, I was just like, no, thank you. How about we go back to talking about just the neutrons themselves, please?
Yeah, you lose me once you get smaller than neutrons.
Do you know why they call the strange quark, though? It's my favorite story. It just, the one scientist was looking, the first one that was looking at how it was,
because it looks at you the wrong way.
Basically, it was like, that's strange, and that stuck. Like it just didn't look normal, and that's why it's called the strange quark. Like
these naming conventions happen in physics way too often, where you just have things that somebody was like, oh, that's weird, and now all of a sudden it's called weird or something ridiculous.
That's exactly what happened with the strange quark.
It happens in fundamental physics more often than you think.
To me, Higgs boson sounds like a band name. I'm going to name my band that.
Yeah.
So for strange names, if anyone ever wants to take has some free time, look at some of the units that we use actually within like nuclear science and engineering. For example, we have something called cross sections, which is like an effective cross-sectional area that a particle will see as it's like of like a target as it's going through a material. It's more akin to like
didn't hear.
Yeah, so it's a cross section. It's short explanation of it is it's the it's like a probability that a particle is going to interact with another one, as a neutron going through a material or something like that. But the unit that we use is cross section.
Cross section.
Oh, cross section.
Cross section. Okay.
But the unit that we use for it is called a barn.
A barn? Did you say a barn?
A barn.
Yep.
Yeah.
That's awesome.
Like hit the broadside of the barn.
As in, yeah. Because you have to remember also that nuclear energy and a lot of nuclear science and engineering comes out of the Manhattan Project. So they were like they actually were intentionally naming things to try and confuse other people so that way their research can get stolen.
Oh,
it's wild.
Yeah, my favorite name along these lines is the banana equivalent dose, BED, which is the effective dose of radiation you get from one banana, which which contain some radioactive potassium.
That's awesome.
I love that. I tell the kids that story, actually, Jeremy. The banana dose?
Yep.
Yeah.
It's great.
So, I mean, we have a lot of these things which can be pretty helpful, because otherwise, if somebody says to you, you know, you're getting 1 sievert, that doesn't mean anything to anybody. Like, that's like, what is that? You know, if they're telling you you're getting half a banana's worth of radiation, you're like, okay, I mean, that doesn't sound too bad. I'll eat a banana happily. And yeah, you can eat a banana as happily as you'd like. But if they tell you something like, you know, the grays that I was just talking about for the nuclear medicine, it's not like it's an inch. You can't just sort of hold your fingers up and guess. You have no idea. There's no context. So people have put a lot of time and effort into, you know, trying to give these things some context.
Okay, sorry, I'm just dealing with a thing on the back end there. Amanda has a question. Panel, can we take one more, or she's gone. Okay, she peaced out. She literally did the peace sign and then she left. So I think I think we'll wrap it up. Thank you so much for being guests tonight. Amazing.
Thank you so much for having us.
Yeah, thank you for having me again.
Yeah, it was so good to hear all of your back and forth chatter. I love it.
This was really fun.
Thank you.
I do have to say,
thanks for showing up, everyone.
Yeah, we had a pretty good crew for, like nuclear. I think sometimes is tough for people who are like, ooh, scary or not interesting. But I find nuclear science so fascinating the more I learn about it. And it's the thing that science communicators like us, we need to get behind in a big way to try and convince people that it's a viable source of energy and it's not going to like melt your face and explode and kill everybody. Because I think the longer we stay away from nuclear, the more dependent we are on coal and natural gas, because we don't have something yet that's like that for full on power all the time. So thank you.
Absolutely. Can I just jump in to say that George earlier said how important it is for scientists to express themselves to the general society, and it just made me think that that's exactly what your Twitter account does. So thank you for bringing this to the general society. Gosh,
yes,
it's so amazing.
Great job, Jason. Yeah.
Well, thanks.
And I don't want to speak for all 3 of us, but at least for myself, if anybody had any follow-up questions, reachable and willing to respond to either DMs or tags on the post or whatever, happy to answer. If anybody has any burning questions that they did not get to ask, usually nuclear people are happy to talk nuclear things. And if anybody has any pressing questions, happy to address that as well.
Yeah, same here.
Same.
Much appreciated. Thank you, guys.
Amanda, you got peer pressured into taking questions by Mairead and Jeremy there.
Amanda's usually the first one to be willing to answer them.
Oh, okay.
Yeah. Yeah.
We're learning more. We're learning more about you guys as we go. All right.
Yeah, scientists are real people.
That's true. We didn't even get a chance to talk about Mairead and Amanda's uranium glasses that they have up there. That was the picture in the nest. But Mairead, I think we had a space where you were one of the hosts, and we did talk about the uranium glasses. Do you remember?
Yeah, we did. We talked about the uranium glasses back on the May 24th space.
Yeah, a month and a half
ago. If anybody has access to the recordings, I did a space on May 24th to talk about some other aspects of nuclear power, and we got to talk about not uranium glasses to see with, uranium glasses to drink out of.
I love it. I think that episode is on the Science Podcast feed, and if not, I'll put it on their special this weekend. So it'll be there so people can learn about it.
Excellent.
All right, so sorry, go ahead, Jeremy. No, go ahead.
I'm just going to say thanks to Mairead. I also ended up with my own pair of uranium glasses as well, so I got to join the cool club.
I love it.
I am a uranium glass influencer, and
absolutely.
Very excited.
Hey, now I want one.
Yeah, me too. I want. Where do we get these?
So there's an interest form, and it is, I believe it's still pinned on my Twitter page. And from the interest form, I can send more information out the next time that the local glass blower here in Knoxville, Tennessee, is going to be doing another round of beer glasses with uranium cane in them. And then there's also a number of pictures on my page. Amanda has a photo with hers that you can also see if you're interested in like looking at the different types of glasses.
They're probably illegal in New York State because everything else is.
I don't think so. Fiesta ware is not illegal in New York State.
Just kidding.
They straight up glow in the dark, though, don't they?
Yeah.
Under UV light.
Under UV light, yeah. They glow under UV, right. Yeah.
Yep.
In the nest, everybody, I put the interest form from Maraid's Twitter account. So as we close up, I just want to say, make sure everybody who is in the audience, give Amanda, Maraid, and Jeremy a couple things. The first one is a round of applause for giving up their time to communicate nuclear science with us. It's pretty amazing. There's a little emoji. You can give them a little round of applause. I made the mistake once of giving somebody like the wave when I was supposed to like be giving them the applause because they look kind of the same. And the second thing is give them a follow. They're scientists that communicate science. If you follow them, they're more likely to communicate more science. And I can't get enough science. So the more people that follow scientists, the better. I don't know if that makes sense. Thanks, George. All right. I think we'll wrap up. And I'll just tell you guys a little bit about the rest of the week. So today we had a special science chat nuclear power panel. Thank you so much, Amanda, Maraid, and Jeremy. We have our common space on Saturday. That's Pet Chat, where we play some games. Our sponsor, I think, has a $50 prize or something. It's pretty awesome. And then you can come talk about your pets. It's not for everybody, but if you want to come have some fun and laugh and see Chris and I have a little back and forth, that's on Saturday at 6 p.m. Mountain Time. Our Science Chat regular starts on Tuesday, so we run that every week. And we have an arachnologist on Tuesday. T. Francis is an expert in spiders. So she studies spiders, she draws spiders, she has spiders. She is so knowledgeable about spiders. And she's staying up till 2 o'clock in the morning because she's in England to come to our space on Tuesday at 7 p.m. Mountain Time, 9 p.m. Eastern. So that's our science guest next week on Tuesday. We'll have more information, but if you want all the information, subscribe to our newsletter. It's like in our profile, and every time I send the newsletter out, I give like a month synopsis of what's happening in science spaces and Pet Chat spaces. So one more time, thank you to our amazing panel. Thank you to all of our speakers, and thank you to all of the listeners. There's many things you could be doing. Watching Netflix, catching up on Stranger Things, watching some kind of sports. I think baseball are the only ones that are going on right now. But you're listening to Nuclear Science, and that's where we want you. So yay. Thanks again. Anything to add, Chris?
No, I just think you need to start a science lobby so you can be as powerful as the lobbyists for coal and natural gas. If we can get one for nuclear, then that would be amazing. Do you have spare time to do that, Jason?
I do not have spare time to do that. But well, normally I have Bunsen bark at the end, but he barked for real. That's hilarious. Normally I have the Bunsen bark, but he barked for real. Okay. All right. Take care, everybody. Be kind, and we'll hopefully see you guys at Pet Chat on Saturday.
Bye, everyone.
Thank you so much.
Amazing
Thanks, y'all.
space.
Bye-bye.
Thank you, everyone.
Bye.